We will solve two more problems on analogy very quickly in this class, and then I have got the feedback that you would probably need some more solutions or problems on momentum integral equation, its use and so on. So, in the remaining one or two classes I am going to spend some time on the concepts that I have covered in momentum integral equation and its solution. So, solution using the concepts of displacement thickness, momentum thickness, and given a profile for velocity inside a boundary layer, how we can use momentum integral equation to obtain an expression for the friction coefficient, shear stress and so on. So, in order to clarify some of the doubts that you have, I will go through the concepts once again with application examples, and hopefully that would clarify any doubts, any remaining doubts that you may have. However, the first problem that we are going to look at or try to solve today is about evaporation from a rectangular channel, from a triangular channel. So, the channel looks something like this, and it's partially filled with water. So, and you have a flow of air along this on the water surface and all the way up towards the length of the channel. So, the channel, triangular channel, where the angle is, the apex angle is 90 degree, is filled with water. You have flow of air on top of the surface of this of the water along this direction, along the length of the channel, and you need to find out what is the rate of evaporation of water from the channel. And can you say something about the rate, whether the rate remains constant or is it, or the flux remains constant? We have to look into that as well. And we also need to find out what is the time required for all the water initially present in the channel to disappear, that means to evaporate into the air which is flowing over it. So, the problem that we have in now is, it's, as I said, it's a channel of triangular cross section, and the length is in this direction. So, we have we have flow of air over the water surface. The temperature of the water and the surrounding air are at 25 degrees centigrade. So, there is no heat transfer that is taking place except for evaporation, and the relative humidity of the air which is flowing over the surface of the water is 50%. The first part of the question is, if the air moves at a velocity of 5 meter per second along the length of the channel, that means on top of the water surface along the length of the channel, what is the rate of water loss due to evaporation from the surface? And the second part is, obtain an expression for the rate at which this water depth, which initially was equal to 1 meter, this water depth would decrease with time due to evaporation. So, rate of decrease of the water depth with time, that is, if the height is z, we need to find out an expression for DZDT. From the above for the above conditions, how long would it take for all the water to evaporate? So, that is the second part of the question. And all the properties of air, namely its kinematic viscosity for the air is given. For water, whatever be the saturation concentration, that is given. Saturation means we will assume that the water in contact with the air, that means over here we have equilibrium present, and therefore, the water is going to be at its saturation value. The density of water is given, and the diffusivity of water vapor in air is also provided along with the value of the Schmidt number. So, it is a rather straightforward problem of flow over a flat surface, which is going to involve evaporation from the flat surface of water, and we need to calculate what is the rate of water loss due to evaporation from the surface. So, I have drawn it in a slightly enlarged fashion over here. So, the flow of air is in this direction parallel to the surface of the water. This flow is taking place with a velocity of 5 meter per second, and the relative humidity is which is denoted by phi, and phi infinity is equal to 0.5. So these are the conditions of the water which is flowing over the conditions of the air which are flowing over the water surface, and the initial height of water in the storage tanks, the triangular shaped, triangular cross section storage tank, is given as 1 meter. So we first need to find out what would be the expression for evaporation, and for expression for evaporation we know that the mass, the rate of mass leaving the surface of water by a phase change mechanism, in which then the water molecules then diffuse into the air having a relative humidity of equal to 0.5, is simply given by the convective mass transfer coefficient, the average value of the convective mass transfer coefficient. Average means entire length of the channel times whatever be the surface area of the water, and you understand that as the water starts to move with time, it will take this shape. So with time the area available for the surface area available for mass transfer will keep on decreasing. So you start with the highest surface area, and then with time this AS will fall, and we have to somehow express this AS in terms of the Z at that instant of time. So we will do that, multiplied by rho A, whatever be its saturation value which is at the air water interface, minus whatever be the value, the mass concentration of it at a point far from the surface. So over here it is assumed that the concentration here is going to be rho A sat, and over here it is going to be rho A infinity. So at a point far from this water surface it is going to be rho A infinity. So we know that this is the expression that we are going to use, but the first step in any problem of this type is to see what is going to be the regime of flow on the surface. Is it going to be laminar flow or turbulent flow? And most likely you would see that it is going to be in a mixed flow condition. So to decide about the relation and or the correlation to be used to evaluate the value of the convective mass transfer coefficient, the first thing one should do is to calculate the value of Reynolds number. So once the value of Reynolds number is known, you decide what is the regime of flow, and then you choose the relation corresponding to that regime. So the first thing that I am going to do is find out what is the value of the Reynolds number. So the Reynolds number value, in this case Reynolds number based on the entire length, is U infinity times L by nu, which is the kinematic viscosity of air, and U infinity is provided as 5 meter per second. The length is 25 meter, and the kinematic viscosity is given as, for the air, is given as 15.71 into 10 to the power minus 6 meter square per second. This has resulted in a Reynolds number of 7.96 into 10 to the power 6. Now this clearly tells you the value of the Reynolds number that you have calculated clearly tells you that it is going to be in the mixed flow regime. So it is definitely turbulent, and the value of Reynolds number is, since the value of Reynolds number is greater than 5 into 10 to the power 5, so therefore it is in the turbulent region, and it definitely, obviously it starts as laminar flow, and then on some point on the surface along the length of the channel it changes from laminar to turbulent. So in order to obtain the average value of the mass transfer coefficient, average value of the convective mass transfer coefficient, one should use the relation corresponding to mixed flow over a flat surface. So I am going to use the mixed flow correlation in order to evaluate H bar m. The relation that we know is a Sherrod number based on length. The average Sherrod number is simply 0.037, that is the constant which we have in the relation. Then Reynolds number, which is 10 to the power 6 to the power 4 by 5 minus 871, this is another constant. If you look at the relation, the correlation that we have seen for the case of from the analogy then for Nusselt number, the relation that we have, I simply have converted that, since the analogy holds, to Sherwood number. So this is Reynolds to the power 4 by 5, 871 is a constant, and it should be Schmidt number, which is given as 0.6. The value of, so this is Schmidt number, the value of Schmidt number is given as 0.6, and the correlation tells me that it should be 1/3. So what I have then here is Reynolds to the power 4 by 5 and Schmidt to the power 1/3. Had this been a case of heat transfer, then Sherwood number would simply be equal to Nusselt number, and Schmidt number would be changed to Prandtl number. So when you do that, the value of this you are going to get is 9616, and therefore the H bar m, the average value of the mass transfer coefficient, should be 9616 times DAB by L. Since Sherwood number is HML by DAB, L is the length scale which is provided to be, which is equal to 25 meter. So this value is going to be times DAB is 0.26 10 to the power minus 4 meter square per second, and for length I know that the length of this water body, this water reservoir, is 25 meter. So the value of the convective mass transfer coefficient is going to be 0.01 meter per second. So this is the value of the convective mass transfer coefficient. And once you calculate the value of the convective mass transfer coefficient, the one that you have to find out is what is the rate of water loss. So you need to find out the rate of water loss, and the rate of water loss, if I express it in terms of mass, which is N sub A is the species, which in this case is water, and N is the time rate of mass of water leaving the interface. So it's simply using something similar to Newton's law. I can write this is as H bar m that I have calculated times A surface times rho A sat, that is on at this point, minus rho A infinity. The only thing I realize here that my AS would simply be equals the length multiplied by this width. So if this is Z, and since this angle is 90 degree, so the base of the water layer, or rather the top of the water layer, must be equal to 2 times Z, because what you have here is something like this. This is Z, this is 45 degree, the entire thing is 90 degree, so the base is simply going to be equal to 2Z. So the surface area which is available for mass transfer would simply be the surface area would simply be twice Z multiplied by L. So this AS is going to be W times twice 2Z, and when you put these units in here, put the numbers in here, this is 0.01 meter per second. For the case of AS, you would get 2 meters, since this is 1 meter, the top one is going to be equal to 2 meter into 1 meter times if I take this rho A infinity is equal to 0, and rho A sat is provided as 0.0226 kg per meter cube, and sorry, this rho A infinity is not 0, rho A infinity has phi infinity is 0.5. So what I can do is I will make one more step, rho A sat outside, and this is going to be 1 minus rho A infinity by rho A sat. This is nothing but this is equal to phi, which is the relative humidity, and which has been provided to be equal to 0.5. So the if I do it once again, it's 0.01 meter per second into 2 meter into 1 meter into the value of rho A sat is provided as the 0.0226 kg per meter cube, and the value of phi is provided as 0.5. So this would be equal to 0.5, and the total is simply going to be equal to the total. When you do this multiplication, this Na would turn out to be 0.00565 kg per second. So what you see here is a straightforward application of the relation, the correlation which is there for turbulent flow, and we know for mixed flow, and the first step is to calculate Reynolds number. This would allow you to choose the right kind of relation which you are going to use either to evaluate Sherwood number or to evaluate Nusselt number. Since this is a mass transfer problem, we are finding out what is the length average value of the mass transfer coefficient, convective mass transfer coefficient. So the value of which we have evaluated, and the rate of water loss from the top surface of the water is by diffusion, because of convective process, since you have flow of air on top of it. So if you use something similar to Newton's law of cooling, the total amount of mass of water which is being lost per unit time would simply be equals HM, a surface, area of the surface, rho a sat minus rho infinity. And when I take the rho a sat outside, what I have here is 1 minus phi, where this is by definition equal to the relative humidity. So you plug in the values of HM, the AS, the rho a sat, and the given value of the relative humidity, and what you get is the amount of evaporation of the water from the reservoir as a function of time. So this is kg, so this is in kg per second, the rate of water loss from the reservoir. But if you look carefully here, what we have in this is AS. So we have a AS in here. So therefore, with time this layer will slowly come down, and as it comes down, the value of Z is going to decrease, and if the value of Z decreases, the length of this layer, the length of the top layer of the surface will also decrease. So this will remain constant, which is the total length of the channel. So 1 meter will remain constant, but this dimension will slowly change with time. So essentially this tells you that the rate of water evaporation from the channel, from the reservoir, may not be a constant. It will depend on what is the depth of water at that instant of time, and that would give you the rate at the instantaneous rate of water loss from the surface. But what happens to the flux? Is the flux going to be constant? So if you look again at this expression, the flux is nothing but Na, which is the rate, divided by the area. So if you divide it by the area, then what your expression would simply be equal to Hm times rho a sat minus rho a infinity. So the flux expression will not contain any surface area. So since the flux expression does not contain any surface area, and the value of H bar m, the length average convective mass transfer coefficient, and the concentration difference, these two parameters will remain unchanged during the evaporation process. What it tells you is that the flux, the water flux, the evaporative water flux is a constant, but since the surface area is changing with evaporation, the rate, the total rate of water which is going from the liquid to the vapor phase, that will vary. So the rate in kg per second will change, but the flux in kg per meter square second will not change. So that's something which we can clearly see from this expression. And now we are in a position to do the second part of it. The second part tells us then what we need to find out is an expression for DZDT, that is how the depth of the water contained in the tank decreases with time, and what is the time, how long would it take to completely evaporate, so that no water will be left in the channel. So, this is something which we have to find out. So, in order to do that, first think of the surface. So, this is my control volume, this control volume of water, and what you are going to have here from is NA, the amount of water which is leaving the surface of it, and which as a result should change the amount of water which is stored into it. Also, the total volume of the channel, which I denote by V, would simply be from geometry Z square times L, where this is Z, this angle is 90 degree, and the length of the channel is L. So, the volume of the water contained in the channel is going to be equal to Z square L, and we understand that with increase with time, the value of Z will keep on decreasing till it disappears, till there is no water left in it. So, this is the volume expression, and we have already seen what is the expression for the surface area. Surface area would be simply twice Z times L. Okay. So, the surface area would simply be equals twice Z into L, where Z is the height of the liquid at any given point of time. So, these are the two factors, two expressions which you would keep in mind. So, if we perform a mass balance, we know that in minus out is equal to the accumulation which is taking place inside this, the rate of change of storage. There is no water which is being added to it. So, the one that goes out, if you look at this, is simply going to be NA, and it is going to be equal to accumulation. So, the accumulation is DDT of rho F, which is the density of the fluid times V. So, the time rate of change of stored water in the channel would simply be given by DDT of rho FV, and this NA, which we have seen before, is going to be H bar M times twice ZL, which is the area, surface area, times rho A sat. If I take that outside, this is 1 minus phi, where phi is the relative humidity and rho F is a constant. So, it is going to be ddt of V. So, ddt of Z square L. So, when you simplify it, what you are going to get is DZDT from this side is equal to minus H bar M rho A sat by rho of the liquid water. So, this is liquid water 1 minus phi infinity. So, this is the governing expression, this is the governing equation which would give you the time rate of change of water stored inside the channel. So, this is DZDT. Now, if you integrate this thing to be equal to this is the density of liquid water 1 minus phi infinity, which is the relative humidity, and integrate it from 0 to T. So, it starts with a value equal to Z, and in order for it to completely dry, its value of Z is going to be 0, and let us say that this is going to take place over a time T. So, the first part of the problem DZDT we have obtained in here. I would also like you to take a look at DZDT based on what we have decided, what we have seen. The DZDT expression does not contain any Z, it contains only constants H bar M, rho h bar m, rho of the flow, rho of liquid water, phi the relative humidity, and so on. So even though Z is not a constant, since the area available for evaporation changes with time, but DZDT is a constant. So the rate changes, but the rate of decrease of the water level will remain a constant, as suggested by the expression of DZDT here. So everything here is a constant. So I integrate it in order to obtain what is the time required for all the water to vanish, and therefore this is the expression. And what you can do then is you find out what is the time required. The time required would simply be equal Z times rho f by h bar m rho a sat times 1 minus phi infinity. And when you plug in the values, all the values in here, so Z start with 1 meter, the rho f is 997 kg per meter cube, the h bar m, which we have calculated to be equals 0.01 meter per second, the value of rho a sat is 0.0226 kg per meter cube, and this is simply 1 minus 0.5. So this T that you would finally get as the answer to the problem is equal to 8.82 into 10 to the power 6 seconds, which is roughly equal to 102 days. So in order to evaporate water present in the channel whose initial depth was 1 meter, it would require, for the flow conditions stated here, approximately 100 days, 102 days to evaporate completely. And so what we have seen the steps that one has to do in order to solve such a problem. The first step is to find out Reynolds number, decide about the relation or the correlation to be used. Then you assume that at the liquid vapor liquid air interface, the air is going to be saturated with the water vapor. So you take the value of rho a sat, the density, the concentration, the maximum saturation concentration of water present in the air at that condition, to be the concentration at the liquid vapor interface. And you know what is the condition far from the interface if you know what is the relative humidity. The relative humidity is simply defined as whatever be the concentration of water vapor at that point divided by whatever be the concentration, whatever be the saturation concentration of water at under that condition. So it's rho a divided by rho a sat, which is denoted by phi, the relative humidity. So you can calculate simply by H a delta C what is the rate, total rate in kg per second of water which is leaving the surface, leaving the container, leaving the channel and getting into the airstream because of the flow of air on top of it. So this gives you the rate, and if you look at the expression, you would see that the rate changes with time with the depth of the liquid, since the top area changes with the depth of the liquid. But when you calculate, if you find or see the flux, when you divide the rate by the area, so your right hand side becomes independent of Z. So the rate changes with time, but the flux remains constant. And then we do a simple mass balance in order to obtain an expression for the height of the water contained in the channel as a function of time. So it's simply the mass balance where the mass is leaving, and as a result of which the total amount of mass stored inside the control volume, which in this case is the channel, is changing. So this gives you a compact expression of time as a function, time required for all the water to evaporate. That means when Z becomes equal to 0, the depth of water becomes equal to 0. So you can find an expression for time, and you see this expression of time after plugging in the values, it would be about 100 days. So this is a nice example of the use of mixed flow relation, correlation, and simple concept of mass balance the equation of continuity to obtain a result for the time required for all the water to evaporate. The next problem which I am going to do is I will just introduce the problem now, and then we will have we'll start the next class. So the problem that we see is we have a microprocessor which is built on a rectangular die. Okay, the size of the rectangular die is 2 centimeter into 1 centimeter, and it's 0.35 centimeter in height. So this is the microprocessor which is sitting on this rectangular die, and the size of which is 2 centimeter, which is L. This is W to be equal to 1 centimeter, and the height H is equal to 0.35 centimeter. It generates heat at the rate of, so you have a Q dot present in the system which is 5 into 10 to the power 5 watt per meter cube. So it's heat generation per unit volume. The chip is to be cooled with air at 20 degrees centigrade, and the chip surface temperature cannot exceed 150 degrees centigrade. So whatever be the case, the flow of cold air should keep the temperature within 150 degrees centigrade, 105 degrees centigrade, sorry, this is 105 degrees centigrade. So what is going to be the velocity of air? The velocity of air over the surface, what should be the velocity of air, and should we orient it like this, where the flow is going to be along the 2 centimeter length, or the flow of air is going to be like this, in which case the flow is along the shorter side, parallel to the shorter side of the plate, in order to obtain maximum heat transfer rate. Okay, so we need to find out the heat transfer, the Q that is leaving the surface as a result of flow, and the flow, is it going to be parallel to L or is it going to be parallel to W? So the question is Q to be max, this V air, is it going to be parallel to L or V air is going to be parallel to W? So that means, is the flow going to be in this direction or the flow is going to be in the other direction? So based on the values of the kinematic viscosity, Prandtl number, and K, thermal conductivity of air given, we have to solve for this problem. So we will do it in the next class.